So we are looking at logarithms today. Chapter 8 is on logarithms and how they relate to exponents and exponential equations. The first thing I want to do is talk about some notation. So you will see this throughout the chapter. We say log base b of x b is the base it is a subscript. And x is called the argument. When we are asked to find log base b, we are actually finding the exponent we raise b to in order to get a value of x. We can think of log base b of x as asking the question, b to what power gives us x? For logarithms, the base b must be positive. So we are only considering positive numbers for b and x. Logarithms and exponential equations are inverses of each other and can be written to give to be equivalencies. They're not the same, but they are equivalent, meaning they have the same values. For instance, so we have log base b of x equals y is equivalent to b to the y power equals x. And we can use this to help us think through different things. So here's an example. Log base 5 of 25 equals 2 is equivalent to 5 to the second power equals 25. These two equations are giving us the same relationship between 5, 2, and 25. Both are saying 5 when 5 is 25 when raised to the second power. And so as we go through and we solve these, we want to be thinking about what base to, or this base to what power gives us this answer. So as we go through these next couple problems, let's think through that. This is really a great connection to what we were just doing in class on Monday. So number 1, log base 9 of 81. Our answer to that comes from asking the question, 9 to what power is 81? Or what exponent do we raise 9 to get 81? So what exponent do we raise 9 to get 81? 9 to what power equals 81? Two. Okay, great. 9 squared equals 81, which means log base 9 of 81 equals 2. How about the next one? Log base 4 of 64. The key is that we want to find a y where 4 to the y power equals 64, or 4 to what power equals 64. 16 times 4 is 64, so 4 to the third. What about number 5? 5 to what power is 1 over 25? Well, we know 5 squared is 25. How do we make that 1 over 25? Negative. Thank you. Yes. So this gives us negative 2. Four is a little bit tricky. Log base 27 equals 3. Three to what power is 27? Let's work backwards. 3. All right, so 3 cubed is 27. So what's the opposite of that? It's not the same as number 3 where it's negative 2, because we're not taking the reciprocal, we're reversing the whole equation. 1/3. Very good, Brian. 27 to the 1/3 power is 3. So log base 27 of 3 is 1/3. And last one, we'll leave that one for workshop. Questions on this page? All right. We have 2 special cases, or not necessarily special cases, but special bases. Special notation. So when we have a base of 10, we don't write log base 10 of x, we just write log x. And this is called the common logarithm. So when we have a base b equals 10, the reason we do this is because our number system is base 10. So we have a base 10 number system. We also have a base of e. Remember that number e that we talked about the other day, Euler's number? Instead of log base e of x, we write ln x. And that is called the natural logarithm. Remember, that is ln, not Some people like to think it's IN. It's LN. It's still a log. It stands for the natural logarithm. So with these, you want to think through the base part first when you don't see it. So log of 10,000 is thinking 10 to what power equals 10,000. So what power of 10 gives us 10,000? With 10, the number of zeros is the number of your exponent. 10 to the fourth is 10,000. With number 2, log of 0.001 just a reminder that the 1 is in the thousandth place. So this means 10 to what power equals 1 over 1,000, which gives us 10 to the negative 3. So y is negative 3 here. Questions on either of those? So 1 over 1,000 is 1 over 10 cubed. 1,000 is 10 cubed. So to get it out of the denominator, that's the negative. So 10 to the negative 3. Other questions? All right, number 3, the natural log of e squared. We use natural log instead of writing log base e of e squared, but that's what it means. So e to what power? E to the y equals e squared. That would be y equals 2. So if I were just looking at this, natural log of e squared, my answer would be 2. For number 4, we're looking at e to what power equals 1 over e to the 10th. And again, remember that when it's in the denominator, you have to make the exponent negative. So that would become e to the negative 10th. So that one equals negative 10. Questions on 3 or 4? If you have log base b of b equals 1, since b to the 1 equals b, essentially we're saying that we're taking, this is like our identity property. You have a base and an argument that are equal. Your base equals your argument. So your exponent or your answer is 1. They're the same. So the answer is 1. Just like you have that invisible 1 exponent. These next two make sense if you consider exponent rules. So when we multiply two exponents together, b to the x times b to the y is b to the x plus y. Here, log base b of xy equals log base b of x plus log base b of y. So when they're being multiplied, we can separate it to two separate logs. And it allows us to work with the logs better. So multiplying allows us to change it to addition. Likewise, division allows us to change it to subtraction. So where we would normally have b of x divided by b of y, and we could change it to b to the x minus y, here we're going to change log base b of x over y to log base b of x minus log base b of y. Property 5 is one of the biggest lifesavers when it comes to being able to solve exponential equations. And all it does is allow us to move an exponent to a coefficient. The exponent of the argument becomes the coefficient of the whole log. And then 6 and 7, we're not going to use until section 8.2 and 8.3. But this one essentially says when the base and argument, or if you have, sorry, let me rephrase that. If you have an exponent and a log with the same base of the exponent, they cancel, leaving any other terms. So here, if we have b to the log base b of n, we're left with just n. Log base b of b to the n, we're left with just n. Don't worry so much about that. We'll explore 6 and 7 next week. For now, we're going to use 1 through 5. And we're going to practice doing these. We are going to do what is called, for number 1, expanding. So we're going to expand on number 1. Number 2, this is condense. And we will have to be able to do both of these things when we solve equations. So that's why we practice doing it on its own. In number 1, we will also replace A for log base A, or capital A, capital B for log base B, and capital C for log base C. But let's go through a couple of these first. So number 1, we have, or part A, we have division and we have multiplication going on. So I'm going to do this in a couple stages. We have log of 1 minus, and I'm going to put both of these in a bracket. Log of A plus log of B. Both of those are being divided. So since they're both being divided, that minus needs to be distributed, or you could just right away write them both as minus. So log 1 minus log A minus log B. Then property 1 says log 1 equals 0. And then in the directions, log A equals capital A and log B equals capital B. And we can drop off the 0 and just write negative A minus B. Questions on this first one? All right, for part B, we need to deal with exponents. Remember that a square root is an exponent, so I'm going to handle that first. We get log of A times B to the 4th times C to the 5th, all to the 1/2 power. And then I'm going to distribute that 1/2 power, which gives us log of A to the 1/2, B to the 4/2, which is just 2, times C to the 5/2. Now these are all being multiplied together, so I can separate them with addition. Log A to the 1/2 plus log B squared plus log C to the 5/2. Then all the exponents can go to the front. 1/2 log A plus 2 log B plus 5/2 log C. And finally, I can replace those logs with those capital letters. So 1/2 A plus 2B plus 5/2 C. Questions on part B here? Okay, putting them back together is a little bit easier. So for part A, actually I'm going to do part A, I'll leave B for workshop. So we have 2 being subtracted, they'll both go in the denominator, and then the first one will be the numerator. But I'm going to first move that exponent, or the coefficient, back to an exponent. So we get log base B of x squared minus log base B of y minus log base B of z gives us log base b of x squared over yz. And that's it. Putting them back together, like I said, condensing feels a lot easier than expanding, at least in my mind. So questions on 2A. All right, we are almost done. There are 2 pages left, but I promise we're going to get through both of them. So this next one, we have these 2 rules here. Remember that logs undo exponentials and exponentials undo logarithms, meaning that they are inverses of each other. And being that they are inverses, remember our inverse functions, if we have f of x and f inverse of x, okay, then the domain of f of x equals log base b of x is the range from g of x equals b to the x power. And we remember that these had a range of 0 to infinity. They had to be positive outputs. So the domain of a log is that you have to have positive inputs. Well, we already talked about the fact that the argument had to be positive. So our argument is positive. And the range of our log is the domain of our exponential functions. And those could be all real numbers. So our log has a range of negative infinity to infinity. Their graphs satisfy the relationship of the reflection over y equals x. And we can see that down here. We have the exponential on the left and logarithmic on the bottom right. We can see they do mirror each other. And we can see the domain and range that the logarithmic has the domain of 0 to infinity with a range of negative infinity to infinity, whereas the exponential had a domain of negative infinity to infinity, but the range had to be 0 to infinity. So we can see that in the graph. And keeping this in mind is going to be very important when it comes to solving, but also when it comes to evaluating our logs on the very next page. So the very last thing we're going to do today is use something called the change of base formula. And this property will allow us to use a calculator to evaluate any function of the form f of x equals log base b of x. Now, if you are using a TI 83 or 84, in the math menu, you can find log base as an option. Then you have no issues plugging this in. You will then put in the base in that base blank that'll pop up. Any other calculator, well, I don't know how to use all calculators out there. I'll put it that way. But your best bet and your fastest bet is to use the change of base formula, which allows us, when we are trying to find log base x of y, to use a common base for both and do log of y over log of x. In other words, log of the argument over log of base. And you make the argument those, and you do it with a common base, with a base of 10, or with using ln. And that way you can do it real quick on your calculator. So instead of having to figure out how do I put in log base 3, I want to find f of 12. So f of 12 is log base 3 of 12. My calculator doesn't have a log base function on it, the class calc. There's a way to get around it, which I'll show you, but the fastest way is just to take log 12 divided by log 3. Because for that, all I have to do is put in log 12, close parenthesis, divided by log 3. I don't have to mess around with trying to figure out the functions. And then that's approximately, it says give 3 decimal places, 2.262. If I use ln, I get the same answer. Can I put in log base 3? Yes. I can take log 10, I can hit the back arrow, and I can delete out the 10 and type a 3. But in the amount of time it takes me to do that, I could have just used the change of base formula. All right. So all 3 of those work. I'm just trying to give you the fastest option. And honestly, change of base is fastest on a TI 83 as well. This was for back when calculators didn't even have all these different options, and you only had common log and natural log. Now, 2 other ones real quick. Number 3, h of -1 is log base 2 of -1. So log of -1 over log of 2. Let's put that in. I don't even need to go any further. Before I even do the second half, it's telling me log of -1 is undefined. There is no solution because we cannot have a negative argument. So if you're asked to plug in a negative number, you say NA because it's not in the domain. Additionally, number 5, Q of t, or Q of 0 equals log base 7 of 0. Let's try typing in log of 0. We get a triangle error. We can't have 0 as our argument either. it's not in domain. Remember, we said that x has to be greater than 0. So 4 and 2 will work. You can try both of those in workshop. I'll give you the answer to number 2. You get negative 0.172, so you can try that yourself. 4, do in workshop if you need to. I will put the homework in soon, but if you have questions, I'll stay on for a little bit. Otherwise, I will see you on Monday. Have a good weekend.